Let's take a look at calculating and interpreting LSD confidence intervals after rejecting the null hypothesis in one-way analysis of variance. Suppose we run a one-way ANOVA and we find significant evidence against this null hypothesis. So we have pretty strong evidence that not all of the population means are equal. But this could mean a lot of different things. Maybe they're all different, maybe mu1 is different from the rest, but the rest are all equal. There's a lot of possible combinations. And we'd like to investigate this a little bit further. One option that we have is to calculate confidence intervals for all of the pairwise differences. So we could calculate a confidence interval for mu1 minus mu2, mu1 minus mu3, mu3 minus mu4, all of those different pairwise comparisons. There are some different ways of going about this, but today I'm going to talk about the method that is sometimes known as LSD confidence intervals. If we want a confidence interval for mu_i minus mu_j, and by that I mean we're going to say mu1 minus mu2, and then mu1 minus mu3, and we're going to do this for all of those pairwise differences. And our confidence interval for mu_i minus mu_j is going to have the same format as things that we've seen before. We're going to take our best estimator of that quantity, the difference in the sample means, and we're going to add and subtract the margin of error. And the margin of error is simply going to be made up of our standard error times the appropriate t-value. And our standard error is given down here. You might notice that this confidence interval format is the same as that of the two-sample pooled variance t procedure, except there's going to be a couple of small changes. First of all, for a pooled variance, we are using the mean square error from the ANOVA table. Mean square error is the pooled variance for all of the groups combined. And secondly, since we are using the mean square error for our pooled variance, we should use degrees of freedom for error for degrees of freedom for the t. Let's take a look at an example that I looked at in greater detail in another video. Can self-control be restored during intoxication? A study investigated this by randomly assigning 11 males to each of 4 groups. One group was given an alcoholic beverage, another group was given alcohol plus caffeine, another group was given alcohol plus they were given a reward for success on the task, and another group was given a placebo drink, a drink that had a misting of alcohol to make it smell alcoholic, but it had negligible alcoholic content. The groups drank their drinks and then took a word stem completion task. Greater scores on this task are indicative of greater self-control. When we look at the box plots, it looks like there might be some systematic differences between the groups. It certainly looks like the alcohol group scored lower than the other groups, and there might be some other differences as well. And we first investigated this by carrying out a one-way ANOVA. And in our one-way ANOVA, we found a very small p-value, indicating very strong evidence against the null hypothesis. Our p-value tells us that there is very strong evidence against the null hypothesis, that it is very unlikely to observe differences like this if there is not some real effect of these different treatments. But the ANOVA doesn't tell us where those differences lie. It simply tells us that there is strong evidence of a difference somewhere amongst these groups, and we would like to investigate that further by calculating confidence intervals for the different pairs. To calculate our confidence intervals, we're going to need to know the standard error, and the formula is given here. The other bit we need to know is that the pooled variance, SP squared, is simply the mean square error from our ANOVA table, this value right here. And so when we want to find our standard error, this is simply going to be the square root of 0.0318 times the square root of 1 over ni plus 1 over nj. And those are the sample sizes in the groups that we're comparing. Each of these groups had 11 observations, so we're lucky here. It's a balanced design, so it's going to be the same standard error for all of the different pairwise comparisons, 11 observations in each group. And this works out to 0.076. Next, we need the t-value. If we're going to do, let's say, 95% intervals, we need to find t.025, but we need the appropriate degrees of freedom for that. And since we're using mean square error for our pooled variance, we should use the degrees of freedom for error for our t. So we need a degrees of freedom of 40, and we go and we find the appropriate value using a computer or a table, and we find that this appropriate t-value is 2.021. And so the margin of error, I'm just going to call that margin of error of our intervals here, is going to be 2.021, the appropriate t-value, times the standard error, 0.076. And that works out to 0.154 to 3 decimal places, although you should carry out many decimal places throughout your calculations if you're doing this by hand. Since we have 4 groups here, we have 4 choose 2 or 6 comparisons that we want to look at. 6 of those pairwise comparisons. And those are simply going to be mu A minus mu AC, mu A, the alcohol group, minus mu alcohol and reward, and so on. And there's 6 possible comparisons. Now we've already got the margin of error for all of these different intervals. So now we just want our point estimate of this difference. So for the A versus AC group, we're simply going to take the difference in the sample means as our point estimate of the difference in population means. And if we take X bar for group A minus X bar for group AC, we'd see that that's equal to minus 0.206. So to get our confidence interval for mu A minus mu C, we simply take this value and we add and subtract our appropriate margin of error that we calculated previously. I've calculated 95% confidence intervals here, and we just worked through this comparison here, alcohol versus alcohol and caffeine. We want to now interpret this interval. And we're 95% confident that the difference in population means lies between those two values. I've starred this interval because it does not contain 0, and in fact it lies entirely to the left of 0. So one of the implications is that we have strong evidence that the mean of the alcohol group minus the mean of the alcohol and caffeine group is in fact less than 0. Or in other words, there is significant evidence that the alcohol group scored worse on average than the alcohol and caffeine group. And we have similar results here when we compare alcohol with the other two groups. So we have the alcohol group having a significantly lower mean than the other 3 groups. The same thing holds for alcohol versus alcohol and reward. The alcohol and caffeine group scored significantly worse than the alcohol and reward group. These other 2 intervals both contain 0, so there is no significant difference in those comparisons. Or in other words, we're saying that it's entirely plausible, say, that mu AR, the reward group, minus the mean of the placebo group is actually equal to 0, in which case there's no real difference between those groups. We're saying it's entirely conceivable, and we don't have any strong evidence against that statement. Let's take a look at that visually. The alcohol group scored significantly worse than these other 3 groups, so these differences between the alcohol group and the other 3 individually were all significantly different. This difference between the alcohol and caffeine and alcohol and reward was also found to be significant, but the difference between placebo and alcohol and reward and alcohol and caffeine, those 2 comparisons did not show significant evidence of a difference. One of the problems with the approach used here is that the chances all of the intervals capture the various parameters of interest can be much less than 1 minus alpha. We're doing each interval at that confidence interval of 1 minus alpha, and we're doing many of these intervals possibly. And so the overall chance that all of your intervals capture the parameter of interest can be much less than that 1 minus alpha. Statisticians have some ways of compensating for this, so there are some other procedures that we use to control that overall error rate of all of those different intervals. A couple of common ones that are used are the Tukey procedure and the Bonferroni procedure, but that's another talk for another day.